In this module, we're going to be talking about even and odd numbers. I'm certain you know what even and odd numbers are, but I'm going to give you a formal definition because it makes it easier to prove mathematical statements when we have formal definitions for things. So the definition here is a number n is odd if n can be written as 2k plus 1 for some integer k. So for example, 3 can be written as 2 times 1 plus 1, and therefore 3 is odd. Notice k can be a positive or negative integer here. And we'll also say that a number n is even if n can be written as 2 times k for some integer k. Again, for example, 0 is even because it can be written as 2 times 0. Simple enough. Now typically we're going to be interested in proving statements of the form p of x implies q of x, or more generally, statement 1 implies statement 2. Okay, so what we'd like to prove here is the following statement. If n is odd, then n squared is odd. This might seem obvious to you, but bear with me. I'd like to give a formal mathematical proof. And you can see that what we're really proving here is that we're proving the statement n is odd implies n square is odd. So we're proving that mathematical statement 1 implies mathematical statement 2. What's the first step when we'd like to prove something like this? Well, it's to assume the first step is going to be, since we want to prove that if n is odd, then n squared is odd, we should assume that n is odd. So assume n is odd. Since n is odd, by our above definition, this means that n can be written as 2k plus 1 for some integer k. Now, what do we want to conclude? We want to conclude that n squared is odd. Okay, so step 2, I'm going to just take n and square it. What does this mean? Well, it means I'm going to take, since n equals 2k plus 1, that's the same as taking 2k plus 1 and squaring it. What is 2k plus 1 squared? Using the FOIL method, 2k plus 1 squared is 4k squared plus 4k plus 1. Okay? Great. So step 3 is I'm going to be factoring a 2 out of this expression. So 2 times 2k squared plus 2k plus 1 is equal to this expression right here that we had just written. But now notice that this means that n squared is equal to 2 times 2k squared plus 2k plus 1. So we've written n squared as a number of the form 2 times this thing in parentheses, which is an integer, plus 1. Let me say that again. We've shown that n squared can be written as 2 times an integer, this thing in the parentheses, plus 1. Therefore, this implies that n squared is odd. Remember, we said that any number that can be written as 2 times an integer plus 1 is odd. This implies that n squared is odd. And that concludes the proof. Let's do another example. Again, I'm going to begin with a definition. We're going to say that a number a is a perfect square if a equals b squared for some integer b. So for example, 81 is a perfect square because it can be written as 9 times 9. Okay, so what mathematical statement would we like to prove? Well, we'd like to prove, so our claim here is going to be the following. If n is a perfect square, and m is a perfect square, then this implies that n times m is a perfect square. So once again, you can see that we're trying to prove something that starts with mathematical statement 1, namely n and m are both perfect squares, and show that that implies mathematical statement 2, namely n times m is a perfect square. So if we want to prove this, what's the first step? Well, the first step is to assume n and m are perfect squares. Okay, what does that mean? It means that n can be written as a squared for some integer a, and m can be written as b squared for some integer b. Okay, simple enough. What should our next step be? Well, since we're trying to prove that n times m is a perfect square, let's multiply n times m. Well, n times m, that's the same as writing a squared times b squared. Right? That's the same as writing a times b times b. This is also the same as writing a times b times a times b. It doesn't matter in which order we multiply the numbers together. So I think you can see now that n times m is equal to a times b squared. Because as we said, from step 3, n times m equals a times b times a times b. And so we can conclude that n times m is equal to a times b squared. Therefore, n times m can be written as some integer, a times b squared. To repeat myself, n times m can be written as a times b, which is an integer, squared. So we can conclude, hence, nm is a perfect square.